sorry. These electrons will get kicked out, leaving a carbon with 3 bonds, and then it'll get attacked. Carbon with 3 bonds. Hey, wait, that oxygen has 3 bonds, and it doesn't want 3 bonds. Shit, that's still a problem. No matter how you draw it, you're going to draw something that your organic teacher would slap your hand and say that's not a real structure. That's the transition state. That, well, this certainly isn't going to work. I better draw another arrow. And by the way, this is where chemists get into very reasonable arguments. I think Dr. Tsai's argument would be, these aren't step 1 and step 2. It's a concerted process, and there isn't really a transition state. Whereas I would argue, no, there is. We can capture and measure the transition states, and we can go back and forth and find evidence one way or the other. The reality is probably a little of A, a little of B. Some reactions don't really have a transition. Some do. Some are quantum. In that Deepak Chopra kind of like, we don't, whatever. But let's go with this transition state theory and ask, why does that matter? And here's why it matters. If we imagine that what enzymes are doing is taking a big activation energy and making it smaller to make a reaction faster, this is what they're binding. They're not binding that. They're not binding that. Here's where the enzyme is doing its job. It's binding that. And this is why most biochemists believe in transition states. If you want to design a drug to mess up an enzyme's day, you don't design a drug that looks like the reactants. You design a drug that looks like the transition state. They're called transition state analogs. They're the most common class of drugs that we've designed as pharmacologists. So it can hop over the hump more easily. Yeah. So let's look at an example of this. This is one of my favorite slides. Austin, I'm glad you're wearing eyewear. Nikki, I wish you had eyewear. This is where I've broken rulers before, so you have been warned. Here is my favorite example of enzymes bind transition states. So we can imagine, here is a stick. Ooh.
Is it a rubber stick?
No. Actually it's already breaking. If I bent it, we can imagine it would break in half, right? And then I would have 2 little sad half sticks. Notice both of those are energy minima. This stick, if I don't touch it, no force is acting on it, will stay a stick. If I break it in half and set those 2 halves down, they will stay 2 halves. But there is a state to go from intact stick to 2 broken sticks that does require an input of energy. I mean, it's not like I'm like sweating here, but I am exerting force to get a bent stick, right? Like there is an input of energy. This is unstable. How do I know it's unstable? If I remove the external energy, it goes back to a local minimum, right? I have to insert energy. I have to push it up the energy landscape. I guess I could put a Bunsen burner on it. Might work. So that's our idea here, right? Now imagine I'm an enzyme that binds the substrate. I'm that good old lock and key model. Bind it all over. Right? How am I going to bend it now? In fact, I've made it harder to bend. I've stabilized every interaction along its length. It's really hard to bend now, because not only do you have to bend me, or it, you have to bend the protein. Shit. Whereas if again, enzyme complementary to substrate, now you've made a state that's even more stable. You just made your activation energy worse. Whereas if the enzyme actually doesn't bind to the substrate, it doesn't bind to the reactant, it binds to this bent in-between state. So if my arm is naturally kinked, and binding involves kinking it, to bind you have to kink, I'm already halfway there. Just a little more force and I'll break this sucker in half. Right? I'm trying, yes. I want it, right? By assuming that enzymes don't bind reactants, but bind this transition state intermediate, we can more readily explain their rate enhancement. This also shows you the principle of induced fit. The ligand has to change shape to bind. And this would be an even more accurate figure if they showed this guy had to change shape a little, right? Presumably the protein is induced fitting as well. It's hard to show that with like whatever. So with things like that. So again, the idea is if I have a natural bend, if bending is the only way to fit, I'm already halfway broken, right? I've already done most of the work. Let's put that from like stick or chair to something slightly more real. Here's a more real example. This, don't memorize, it's an example to guide you, is how peptides are broken down in our stomach. So the enzyme chymotrypsin that breaks down protein you eat has a whole big structure, but it has some important amino acid residues. An aspartic acid at position 102, a histidine at position 57, a serine at 195, a glycine at 193, and another glycine, oh, that's the same glycine, sorry, glycine 193. And what it's showing is if you have a peptide, so let me orient your eyes. In red is the peptide you ate for dinner. Nom, 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 nom. There's a peptide bond right here, right? So we've got our phenylalanine, and then a peptide bond, and then down here we'd have some other amino acid. The R group would continue. There's the peptide you're eating. Breaking an amide bond is really cruddy hard. But to do it, you'd propose a mechanism like this. Like you'd have an oxygen attack the carbon and swing some electron density out to the carbonyl. How would I make that stable? Well, what if I had a nice space where that excess electron density could go? What if my amino acids are arranged so that there's some nice hydrogen bonding pairs ready to bond to a negatively charged oxygen? There's no negatively charged oxygen in what I'm binding, but my amino acid R groups are arranged as if there is already a negatively charged oxygen, to pull it that way, to promote it that way. And that here's the idea, is that when you form this negatively charged oxygen species, you're already ready to stabilize it. You've got bonds in place. If you looked at this structure, if you looked at your substrate, you would never guess, you would never assume the enzyme would have bonding groups here. Because the enzyme doesn't really like to bond to this. What the enzyme likes to bond to is the transition state. And it turned out this was a tipping point. This was really a revolution in pharmacology in the 1970s when we realized if we designed drugs to look like our hypothetical transition states, they work a lot better than when we were designing drugs that looked like substrates. And so now if you look, most drugs that have been rationally designed, like we wanted to put this methyl group here, are called transition state analogs. They look like transition states. Here's that same mechanism from a different book. I don't necessarily like it as well, but just trying to show. We've got a peptide bond that we need to break, right? We'd like to break this peptide bond. We're going to do it with some sort of nucleophilic attack, but that'll generate this oxyanion, this tetrahedral oxyanion intermediate. And what we really need to do is stabilize that so that this can actually happen, because it doesn't like to. This carbonyl is quite a bit more stable than this weird tetrahedral guy. So we need everything we can to stabilize that intermediate. And once we stabilize that intermediate, we can move forward and do all sorts of fun stuff. And we'll look at enzyme mechanisms more soon. Like not today, but soon. And so that's a big idea, is we want to bind to or stabilize the transition state. How do we do that? How do we do that? We're going to need some real examples of how do we stabilize this? And I tried to show one or two so far. This idea that we could have some hydrogen bonding partners available so we could have the right R groups there. But there's other tricks we pull. Things like using metal ions. or using organic molecules. And it turns out these can matter a whole lot. So for example, DNA synthesis, to take two pieces of DNA and join them together, if you look in the active site of the DNA polymerase, to extend our DNA and replicate it, it requires the metal magnesium. You have to have magnesium. It's why it's in multivitamins and stuff, to make new DNA. Understanding that as a stabilization of the transition state of the complex, you can add chemicals that pull away and sequester, trap magnesium to things like Coke so that bacteria can't grow in it. So if you look at most Coke cans or products, they'll have a chemical called EDTA. EDTA's only job is it binds to magnesium really, really well. Which means if there were any bacteria from the assembly line worker who was making the Coke cans or whatever, it can't grow in your Coke can because it has no magnesium. It can't stabilize the transition state of DNA synthesis, and you're done. That's cool, right? That we start to see. And by the way, this is why I put organic molecules. The coolest thing that I think, personally, I'm going to show you over the next 8 weeks, is that how long we have left? 7 weeks? Somewhere there. Is that every vitamin you eat is just sitting in an enzyme pocket, binding the transition state. Riboflavin, is in the transition state complex in the electron transport chain, allowing electrons to flow into your mitochondria, or through your mitochondrial membrane. Biotin that we eat, is used to synthesize an intermediate for the citric acid cycle called oxaloacetate. Every vitamin, the reason they're vitamins is they need to fit in and stabilize a transition state. That's why we eat them. That's cool to me. So we're going to start digging into that. Thank you. Today was a lot of math and a lot of where are we going? On Wednesday, we're going to spend some time on a review session for the quiz. We're going to calm our nerves. But I sent out a revised study guide. I encourage you to start taking a look at it. Spring break is meant to be a break. I didn't suddenly add a whole bunch of new material being like, you'll study over breaks, suckers. I want you to take a break, but that means you got to study now. Suckers. Hello, hello. Okay. There's no stupid questions. See you later. Oh no, that's a really smart question. Both in different cases. Some enzymes are thought to facilitate an already existing transition state. Some enzymes are thought to encourage or force a new novel transition state.
Okay, because I was looking at the STIP model.
Yeah. So it depends on the enzyme. Some do and some definitely don't encourage something new. They're just kind of reinforced with So, yeah. What? Hello?
So I got your email about
I just bought it today.
Yeah.
I should be taking that many grams a day.
I thought I said that. I think it's too early.
Yeah, you did.
It's just saying it. So,
I wasn't expecting.
No judgment.
Posters.
No judgment.
Okay.
yes.
Cool.
Austin also was like, oh, not quite there yet.
Especially since I'm not even starting until after spring break.
Yeah. So don't worry about it.
Okay, thanks, Dr. Bottom.
You were just on my mailing list now for the lab. So I didn't want you to be like,